All right, folks. In this video, we're going to talk about atomic orbitals. And more specifically, we're going to take a look at how those atomic orbitals look like, their orientation and their shape. Okay. In the second topic, we talked about the quantum numbers, and we learned how we use the three quantum numbers to define atomic orbitals, right? Especially ML. We said that the number of the atomic orbitals is defined by the number of the ML values. For instance, if you have 5 different ML values, then you will have 5 atomic orbitals. Okay? All right. First one, 1s orbital. Okay? Well, remember when you have 1s orbital, that tells us n equals to 1, L equals to 0. Remember the S represents L equals to 0. Okay. This is how 1s orbital looks like. Essentially, it's a sphere with a blue surface. Okay, with a blue surface. Well, you may ask me, how do you know it's such a sphere shape? Well, the answer is based on the calculation. You can calculate the shape of the atomic orbitals based on their wave functions. But these calculations are not our concern. So don't worry about that. Well, the picture on your right side is the radial distribution function. What does that mean? Okay, let's just break this picture down into small parts and explain that one by one. First thing is the x-axis. X-axis is the distance from the nucleus. Okay, so for instance, if you have a point right here on the x-axis, the x-axis on this picture represent the distance between this point and the nucleus. Okay, the y-axis on this picture is a total radial probability. Okay, it means the chance for you to see an electron or electrons. Okay, when you move around on this atomic orbitals. Okay, and now if you combine the x and y axis, the meaning of this picture tells us when you move from nucleus outward, okay, what the probability you will have for you to see electrons in an atom. Okay, when I draw an arrow on the y-axis, but essentially you can be any directions, z-axis, y-axis, x-axis, or any directions among the three. Okay, it doesn't have to be the y-axis. But anyway, so when you move from nucleus outward, you can see that the chance for you to see electrons dramatically increase. And when you reach the distance of 52.9 picometer, remember picometer is a very small distance. Okay, when you reach this distance, the chance for you to see electrons reach its highest point. Okay, in other words, electrons will move around on this 1s orbital. Okay, almost randomly with the speed of light. So where can you find out the electrons with the highest chance or highest probability? Well, the answer is when you have a distance from nucleus of 52.9 picometer, you can see these electrons, okay, with the highest probability. Okay, well, essentially that means for 1s orbital, okay, you can find out the highest electron density on 52.9 picometer distance. So that's why you can see this kind of spherical shape of this 1s orbital. Okay, so this is 1s. How about 2s and 3s orbitals? Well, according to the calculation, they all have this kind of spherical shape. Okay, But one thing is different. If you, this is 2s, this is 2s orbital, okay? So 2 means n equals to 2, s still L equals to 0. 3s, n equals to 3, L equals to 0, okay? For 2s orbital, if you cut it open, you can see two layers. The central part here and the one layer around the central part. Between the two parts, there is a wide area. Okay, so what is this wide area? Well, the wide area is called node. N-O-D-E. Okay, the node is an area in which the probability of finding the electrons is 0. In other words, in this wide area, you cannot see any electrons, okay? Because electron will not get into this wide area, okay? And how about 3s orbital? If you cut it open again, you will see actually it is a like an onion, okay, a bigger onion. In this case, you have the larger layer, a middle layer, and the core here, okay. And then in this case, you have two areas with white color, okay. And again, these are nodes, okay. Electrons will not get into these wide areas, okay. This is 2s and 3s orbital. Okay, 2p orbital. Okay, 2p orbital means n equals to 2, L equals to 1. Okay, and we know from our discussion regarding quantum numbers, when L equals to 1, ML would have three values: -1, 0, and +1. So based on the number of the ML values, okay, three values, that means three atomic orbitals can be defined, if you happen to remember what we had in topic number 2. All right, that's why you see these three 2p orbitals. Okay, this is px orbitals, and this is a py orbitals, and this is a pz orbitals. Why do they have different names? It depends on the positions of those bubbles. Okay, in chemistry or in physics, the name of the term for this bubble is lobe. Okay, let me write it down here. Lobe. Okay, so you have two lobes here, two lobes here, two lobes here. For px orbital, both lobes are on the x-axis. For py orbital, both lobes are on the y-axis. For pz orbital, both lobes are on the z-axis. This is a difference. Okay. Now the 3d orbitals. Okay. Now 3d, that means n equals to 3, L equals to 2. Okay. When L equals to 2, there are 5 ML values from -2, -1, 0, +1, and +2. 5 different ML values represent 5 orbitals. That's why you see these 5 orbitals here. dyz, dxy, dxz, dx squared minus y squared, and dz squared orbital. Okay. Again, the difference among the 5 d orbitals is the position of those lobes. Okay. For the dyz orbitals, 4 lobes, these 4 lobes are sitting on the yz plane. Okay, so it's defined as the dyz. For dxy, the 4 lobes are sitting on the xy plane. Okay, for dxz, 4 lobes are on the xz plane. dx squared minus y squared, okay, this is going to be different because you will see that the 4 lobes are on the x and y axis. Okay. For dz square orbital, you can see there is a donor ring here, and above and below the donor ring there are two lobes. These two lobes are on the z-axis, and this donor ring is on the x and y plane. Okay, I want you to be very clear about the difference among the 5 d orbitals. All right, f orbitals. Well, it's getting more and more complicated, as you notice. For f orbital, that tells us n equals to 4, L equals to 3. And when L equals to 3, let me write on this side, and ML will have 7 different values from -3 to -2, -1, 0, +1, +2, +3. 7 different ML values, 7 different F orbitals. Okay, and you can see that they have different shape, different orientation, and different lobes. Okay, those F orbitals are not required. Okay, I don't need you to remember how they look like. But for the S orbital, P orbitals, and d orbitals, the orientation and the shape, these are required. Okay, so let's do some quick practice. Which type of orbital is represented by this picture? Well, you can see that if you are familiar with those S, P, D orbitals, you will immediately realize that, okay, this one looks like a P orbital. Okay, so the answer is going to be A, P orbital. In this case, let me highlight that. Okay, going to be P orbitals. Question number 2, which specific orbital is represented by this picture? Well, okay, you can see that this one, donor ring here and 2 lobes on the z-axis, and again, it's one of the 5 d orbitals. Okay, and more specifically, it's going to be the dz square orbital. Okay, so the answer is E. All right, if you have any questions, let me know.